relatively newborn star cluster. Okay, so we will see some nebulae where it is reflecting, and if I've got my slides in the order I think I have them, and some in which it is emitting. Okay, this is the Orion Nebula. This is called an emission nebula. Reflection nebula, emission nebula, okay? Emission nebula, the gas here is heated up to such a temperature that it glows on its own, okay? This takes really hot stars and high energy radiation. Not visible light radiation, but ultraviolet radiation. So the ultraviolet light from the hot stars in the center heats the gas until it glows. All right, is this what it would look like to the human eye? No, it's not. It's a Hubble image. Hubble takes very specific filters, and it's not a simple RGB image. In truth, this emission nebula would be generally just pink, that pink of hydrogen alpha. Remember that one line that I said was the 3-to-2 transition in the hydrogen spectrum? That's the dominant emission line in the whole universe, because hydrogen is the dominant element in the whole universe. So that pink of hydrogen alpha is the dominant color of emission nebulae in the universe, okay? So if we looked at this, all of the glowing gas to the human eye would appear pink, all right? There are some wonderful images by Dave Malin, which were the dominant images before Hubble of the universe, and a lot of them are just pink and blue. Pink for the emission nebulae, blue for the reflection nebulae, because of course blue light scatters better on the reflection nebulae. Okay? All right, what about this? This is the Crab Nebula. We studied this on our multi-wavelength things. Is that emitting light or is that reflecting light? How could you tell? All right, I'm not actually expecting you to know the answer. What would you need to know? Temperature. Temperature needs to be where?
Higher to emit.
The higher the temperature, the more likely it's actually emitting. If it's 10 degrees, if it's room temperature, it's not emitting visible light. If it's thousands of degrees or above, it can be emitting visible light. Okay, this one actually is emitting light because this is a supernova explosion. The gases were heated by that explosion, so it is emitting visible light. Okay, we also see galaxies. All right, most of what we're seeing in galaxies are these star clusters. You see the blue stars along here. You see these red star clusters. This is that pink of hydrogen alpha that dominates the universe in the emission nebula. Every single one of these pink dots is an emission nebula. It's a star-forming region. Okay? All right, this is our pink and blue. But we will also note there is stuff in the universe that's not. See this dark stuff? All right, you see that dense gas there? That's dark. That's opaque to visible light. It's not emitting visible light, okay? It will show back up when we look in the infrared, okay? All right, so visible light. You may have learned this, or you may even teach this, red, orange, yellow, green, blue, violet, Roy G. Biv. It used to be when, a little before I went to school, Roy G. Biv with indigo as a color. Okay, did you learn indigo as a color?
I did too.
Yes, how many people learned indigo as a color? Okay, indigo was removed, oh wow, more than usual. Indigo was removed as a color decades and decades ago. I guess you guys use old textbooks, okay? All right. Does anybody see an indigo in here? I don't see any indigo between blue and violet. Okay. That is the standard way that we remember this, right? Roy G. Biv. Okay. Or Biv if you want to include indigo and be retro back to the 1960s. Okay. All right. Here's the important stuff to remember about it. Basic physics of light. Going from red to violet, or violet to red. We think of red as long wavelengths, violet as short wavelengths. So wavelength increases to the left here. All right, in the way we normally memorize it, wavelength increases to the left, energy increases to the right. Low energy, high energy. That also means that increasing frequency, low frequency, high frequency. Energy and frequency are proportional to one another, okay? So here are the basic equations of the physics of light. Energy is proportional to frequency. E equals h nu. Okay, that is the Greek letter nu, that's not a V. But in PowerPoint, they look exactly the same, at least in this font. I'm sorry about that, okay? Energy is measured in joules. We use the letter E for it. H is Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. Okay, you don't really need to know all this stuff, but there is just a simple constant of proportionality, all right, named after Max Planck. All right, and frequency is in oscillations per second, hertz, which is the Greek letter nu, okay? So, joule seconds times per second equals joules, so our units work out. All right, energy is proportional frequency. So a high frequency will have a high energy. Something with low energy will have a low frequency. Good. All right. Frequency, I have found in my teaching, is more difficult for people to understand than wavelength. Okay? So I like to think of things as energy and wavelength because I think that that's how people understand it better. If you can explain frequency, you are better than me. I mean, you need to know frequency, okay? But I tend to think that in the public vernacular, energy and wavelength work better together. All right? Frequency and wavelength are inversely proportional. Frequency times wavelength equals the speed of light. Okay? Fundamental characteristic. All right? Nu times lambda equals c is the equation that you'll see. All right? Where frequency, again, hertz. Wavelength, the distance between the crests of the wave, all right, can be measured in meters, whatever meters you want, whatever version of it, and we use the Greek letter lambda. And finally, the speed of light is a constant, approximately 300,000 kilometers per second, so close to 300,000 kilometers per second that you're only making less than a 1% error if you use 300,000 kilometers per second, okay? For those of you who want to use English units, 186,000 miles per second, all right, it has been given C. All right? So if anybody asks you, hey, what's new? You can say, oh, it's C over lambda, okay? Yes, physics jokes. At least somebody in the back of the room likes that. Okay. Okay, so frequency times wavelength is speed of light. You can also then turn wavelength as being inversely proportional to frequency and inversely proportional to energy. All right? So if we look at the visual spectrum in increasing wavelength, then we're going from blue to red. Okay, we take that as part of the full electromagnetic spectrum. We have our high energy down here. We have our low energy up here. So shorter wavelength, higher frequency, larger energy. Longer wavelength, lower frequency, smaller energy, okay? Just getting the way those work is an important thing to get in your head. Okay, great. Now let's go have a trip down that electromagnetic spectrum and see what we can find. All right, I will say that I have put on this the adopted rough range separations between the various pieces of the spectrum. Okay, if you talk to people who are absolute fanatics about this, they will argue on this, all right? Do not take what I have up here as gospel, but they are all very good approximations to where you want to draw the line between them. Is there really an exact line between radio and microwave? No, it's just a continuous spectrum. So where we put these points is somewhat arbitrary. But if you have a receiver that goes from here to here, well, then if that crosses a border, who cares? You still call it a radio or you still call it a microwave receiver. All right, doesn't matter. But here are the rough boundary lines between them, okay? Wavelength greater than 1 meter. Okay, so think this is a wavelength, you know, that big. It goes up and down. That's kind of cool, all right? The radio waves. Frequency less than 300 megahertz. All right, megahertz. Mega means million. 300 million cycles per second. Okay? So you got this big, and it's going up and down 300 million times a second. You got a radio wave. Okay? Fun to think about those numbers. But what do those numbers really mean? Well, in our parlance of it, we think about AM radio. AM stands for amplitude modulation. You're sending the signal by changing the amplitude of the wave. Okay? If you look on your dial, you go from 540 to 1600. The units actually are kilohertz. All right? Kilohertz. So the most listened to AM radio station in the country is WABC AM 770 in New York City. That's 770 kilohertz, which is 770,000 hertz. Okay, so that is what's happening in your AM radio has to be sensitive to that. Your FM radio, FM stands for frequency modulation, so you're changing the frequency of it just a bit in order to send your sound signal across it. That's 88 to 108 megahertz. Okay, and you need a little band around it because you're going to change that frequency. You may be broadcasting at 88.3, but you need a little bit below it and a little bit above it to do that frequency modulation, right? Okay, that's why you won't see 88.3 and then 88.4 and 88.5. You'll see 88.3 and the next one will be 88.7, right? They usually allow 0.4 in between radio stations in the same market. Okay, that may be an FCC regulation to give that. Okay, the most popular, most listened to FM radio station is also in New York City. You might understand why. It's WPLJ 95.5. That stands for 95.5 megahertz, so 95.5 million hertz. Okay? All right, so 95 million hertz is a low frequency. All right? 95 million hertz is a low frequency, which means if I gave you the frequency of visible light and other things, all right, the numbers would be going to get astronomical. So I'll stop doing frequency after a while. All right. In terms of astronomy, well, we look at Jupiter, and we talked about Jupiter not emitting invisible light. Okay, but Jupiter has a large magnetic field around it. Okay, Jupiter is the largest planet. It has a giant magnetic field. That magnetic field is larger than our sun. If you take the volume of that magnetic field, it encompasses a region of space larger than our sun. Inside that magnetic field, along magnetic lines, you have electrons bouncing up and down. All right, those electrons bouncing up and down emit a decameter, tens of meter radio waves, radio waves with wavelengths in the tens of meters. And you look at Jupiter in the radio, and you see this. All right, because when you look, you get the edge-on effect, so that you can see these are the places within the magnetic fields where those electrons are bouncing up and down as they go around there. So Jupiter is a radio source. Normally you would not think of a planet as being a radio source. It is actually the electrons in the magnetic field that is the radio source. The Whirlpool galaxy, all right, that is also a radio source. All of that low-density gas in there, there is hydrogen, okay? But it's actually, what is really cool, I love this image because we have to take that Hubble image and shrink it down to here, and then we're going to take an optical image and overlay the radio view of the hydrogen gas. That's the full extent of the hydrogen gas in the Whirlpool galaxy. What we are seeing here is the radio emission from neutral hydrogen, what astronomers call H1. Okay, the neutral hydrogen has a radio frequency emission that we can tune to and find out where all that low density gas is in the Whirlpool galaxy. And while you can see the spiral arms here, you can definitely see that there's a big long thing here that almost assuredly was induced by an interaction between galaxies. You can see this small galaxy up here is actually passing by. At some point, either that galaxy or some other galaxy pulled off some material to create this big, long tidal tail. We'll talk about tidal tails on Thursday. All right, this is Cassiopeia A supernova remnant. We've talked about supernova remnants a bunch of times. Explosions, incredibly high energy explosions. But radio waves are low energy. Why would we have radio waves from them? Because as this explosion plows into the medium around it, the energy is going to cascade down. All right, and so here is the radio emission from it. As that supernova explosion plows into the interstellar medium around it, energy cascades going from the high energy, which we'll see later. All right, this one here is a visible light, but all the way down to radio waves on the edge. Hi, Evelina. How are things?
Good.
All right. Did you have anything you needed to interrupt us on?
No.
Okay. You're just here. All right. Just want to talk to John. Great. All right. So that's radio for that. Finally, the last one we want to talk about is a active galaxy. All right. So this is a beautiful image. It's a combination of Hubble image, all right, which is the black and white type stuff. And you can see there's a galaxy here. All right. This is a giant elliptical galaxy. And at the core of all large galaxies, we believe there is a supermassive black hole. Okay? Very, very tiny thing. It's about the size of a solar system. A supermassive black hole at the core of this giant elliptical galaxy. But these supermassive black holes, they have disks of material streaming into them, okay? Just like that neutron star we showed you, that picture of the disk. And this stuff is creating incredible high energy stuff, but as it's spinning, it creates a spin on the magnetic field. That magnetic field then flings things out in these oppositely directed jets. Those jets are so powerful, they can extend not across interplanetary space, not across interstellar space, but across the entire galaxy and out into intergalactic space. We're talking something the size of a solar system extending out jets visible in radio light for 5 times the radius of the entire galaxy. So in radio, as that high energy jets slow down and encounter the intergalactic medium, they give off energy at low energy, they give off some of their energy at low energies, and you can see these giant radio lobes. This was one of the craziest discoveries of astronomy in the mid-20th century, was that you looked at these relatively small galaxies, and you saw these giant emission lobes of material coming out. All right, and the only thing what powers them is a supermassive black hole way down in the tiny core of that. Okay, kind of cool. That's what we see in radio. Microwaves. Microwaves, the wavelength goes from a meter at the radio end down to a millimeter at the infrared end. That means the frequency is between 300 megahertz and 300 gigahertz. Giga meaning billion. Okay? So now you're talking some serious numbers of frequency. All right, microwaves. How do we know microwaves in our daily life? Because we have microwave ovens, okay? This actually is one of the really old ones, 1970s, I think, the radar range by Amana. Okay, maybe you grew up with one of those, okay? How does microwave oven work? Okay, microwave ovens work by dielectric heating. What it actually does, water is a dielectric molecule because there's a net positive versus negative on, it's not symmetric, right? We got the oxygen and the 2 hydrogen, and so it is polar in it's not spherically symmetric in its electric charge. So it can have a net positive and electric that you can actually start to spin. All right, if you put an electric field on something and generate magnetic fields within the molecule starts to spin. All right, and that's dielectric heating. Okay, they use a frequency of 2.45 gigahertz, which is a wavelength of about 12 centimeters. For consumer level ones, I'm told that the professional ones operate at 915 megahertz, which is a wavelength of about 32.8 centimeters. Okay. So those are both in the microwave range, and that's how you heat your food. Using, you can tell go home and as you reheat your dinner tonight, you can say, hey, I'm using 2.45 gigahertz radiation to get the water molecules in my food spinning fast enough to heat things up. And then your family can look at you like, you're such a geek. Okay, trust me, I get it all the time. All right, let's go back to that Whirlpool galaxy. I told you it's one of my favorites for doing this. All right, this is what the Whirlpool galaxy looks like in visible light. All right, and in microwaves, we see the very, very densest core of that dark gas. Let me go back to visible light. You can see all that dark gas along here. All right, we see the dense core of that visible gas. Why do we see that in microwaves? Well, because there is a transition in carbon monoxide. Okay, it's the J12 to 13 or something, or 3 to 1 transition of carbon monoxide that radiates at microwaves and is easily detectable. And we have found that carbon monoxide, CO, this transition, is well correlated with the densest hydrogen gas, the hydrogen molecular gas in galaxies. So instead of trying to find the hydrogen gas by looking for hydrogen emission, we actually look for the densest gas in galaxies by looking for carbon monoxide emission. Okay, so the CO emission here allows us to see the places where the gas is truly dense. If I go back here, you can see that we've got some here along in here, all right? You can see that it's darker here, not quite so dark here. That actually is reflected. You get a little bit more density here and here, not so much along in here. So those spiral arms are not of uniform density along the length of the spiral arms. You start to understand the structure of the spiral arms. As you might expect, they're densest toward the center. They get less dense as you go further and further out. But you can also see that they are clumpy in nature along the length of those spiral arms, something we learned from our CO observations in microwaves. All right, we also can look at disks of material around stars. Now, this is a star whose phone number I forget, something like HD 107, yes, HD 107146, okay? Well, actually, this is not a picture of the star. It's a picture of the debris disk around it, okay? The star was here, and we blocked it using what we call a coronagraph, okay? Have you ever driven down the road and there's the sun shining in there, and you put your hand up to block the sun, right? Or you pull your car visor down to block the sun, right? That you're blocking the light of the sun so you can see the fainter stuff around you, right? Here we block the light of the star so we can see the faint stuff around it. That's called coronography. And so there are these disks of material around young stars. All right, we can see some detail with Hubble. This is probably in the infrared. It doesn't say on my notes here, but this is probably in infrared. All right, if we use microwaves to look at it, we will see even more detail because we'll get deeper and deeper into it. All right, so this star HL Tauri, which is right up in here, this is the visible light image from Hubble. With the Atacama Large Millimeter Array in microwaves, we see this. All right, now this is not an artist's drawing. This is an actual image of the disk of material around the star HL Tauri. Okay, look at these absolutely sort of beautiful sort of racetrack-like structures, this bullseye structure. This is a disk of material around a newly formed star, and there are most likely planets forming in that disk. Those planets, their gravity from those planets will have cleared out gaps within the disk. Look at all those beautiful gaps. All right, now that doesn't mean that there's a planet in every one of those gaps, but it does mean that there is gravity of a planet creating that void. There needs to be some sort of gravitational disturbance. Now, it could be that there's a planet out here and there's a resonance between here and here creating this gap in here, or there could actually be a planet in there creating that gap. We are not sure, we cannot tell from these observations, but we are seeing the process of planetary formation in microwaves around this star. And I got to tell you, this is the first high-res image from the ALMA array, and it blew the entire astronomical community away when it came out last spring, because we had never, ever seen a disk of material around a star in this kind of stark relief and saying, yeah, there are gaps. This is how planets form. Kind of cool. The last thing about microwaves is that they tell us a lot about the universe. All right? So if we look at the entire night sky in microwaves, we get a uniform emission across the entire night sky. It's about 3 degrees Kelvin, okay, in terms of the temperature that would be required to emit it. If we subtract off that uniform emission, we get a hot spot and a cold spot. Well, that's actually Doppler effect that measures our galaxy's motion through the universe, because it's a little bit hotter over here, a little bit cooler over here, because we're moving through the universe towards it. So we actually measure the galaxy's motion through the universe in microwaves. All right, we subtract that off, we see this. All right, this is, you can see, the plane of our galaxy. All right, which sort of interferes with the stuff that we're trying to look at. So we subtract off that galaxy, getting that out of our microwave observations, and we get a plot that looks something like this. This is what we call the cosmic microwave background. Now let me explain it to you because it's really important. It won a Nobel Prize, by the way. All right, so the universe started out small, hot, and dense. It has expanded, cooled, and become less dense since then. There's a point in the early universe from which the last light leaves the early hot universe and dense universe. Once the universe goes from being so dense it's opaque to being transparent, and we call that the surface of last scattering. And it occurs about 500,000 years after the Big Bang. So, from that last scattering surface is emitted an imprint of what the universe was like 500,000 years after the Big Bang. What you are seeing in microwaves is that radiation started out at around 3,000 degrees, cooled down as the universe expands. We know Boyle's law, PV equals NKT. As it gets bigger, it gets cooler. The universe has expanded about a factor of 1,000 since then. So it went from 3,000 degrees to down to 3 degrees, observable in the microwave. And what we see in the spots here are the density inhomogeneities imprinted from the universe. So if it's a little bit more dense, it's a little hotter. If it's a little bit more rarefied, it's a little cooler. These are variations in the temperature of the universe 500,000 years after the Big Bang at 1 part in 100,000. Okay? So the variation in the universe with 1 part in 100,000 is the density inhomogeneities that led to the galaxies, stars, and planets we see today. This is the initial state of the universe that gives us the variation on how structure formed. And this won the Nobel Prize first of all, for Penzias and Wilson, who discovered it. It also won the Nobel for who discovered, first of all, this. Penzias and Wilson won the Nobel Prize for getting that. Okay? John Mather here at Goddard Space Flight Center won a Nobel Prize for getting this, seeing that variation in it. They have since done the WMAP experiment to refine that, and then the Planck experiment to refine that. All right? We now are able to study the density variation in the universe 500,000 years after the Big Bang and use that as the initial conditions for where the universe started. Okay? Really cool stuff. All right? And the cosmic microwave background, I could probably do an entire lecture on it, but we don't have time, so let's move forward. Any questions on that before I move on? All right, let's go forward to infrared light, okay? We're talking wavelength. I'm going to skip frequency now. 1 millimeter down to 700 nanometers, okay? So millimeters to micrometers to just less than micrometers, 700 nanometers, all right? Now, first of all, people will tell you that night vision is infrared vision. It's not. All of these military things that you see, or in Call of Duty when they flip on the green thing, that's not infrared view. That's actually just enhanced low light vision, okay? All right, and when you see this, that's not infrared. That's just amplifying the visible light that's available, okay? What is infrared vision? Do I have it? It's thermal vision, which we showed you here. So here is that pic of the fireman looking at this smoke-filled room. Thermal vision, heat radiation. You can see the heat of the fireman. You can see the heat of the person prone on the floor. We had, of course, the infrared camera thermal vision demonstration here. I don't need to go too deeply into that. But we use it in astronomy. The comparison for Jupiter, Jupiter actually emits at the infrared. We talked about Jupiter. It doesn't emit at visible wavelengths, right? But it does emit at infrared wavelengths. Jupiter is actually an emitter at infrared wavelengths. Here is the visible light image. You can see the stripes on it. You can also see the stripes here, right? Remember how we talked about the cloud tops being at different levels, okay? You can also see that the energy is escaping at different levels in the atmosphere. Okay, I believe it is the higher level clouds are the ones that give off more of the infrared heat where the heat is escaping. You can also see these little dots here, right, to correspond to these storms. All right, these storms are places where energy is escaping from Jupiter's atmosphere. Let me check. Am I using this image? All right, and in particular, the largest storm on Jupiter is the Great Red Spot. And there's also Red Spot Junior, if you didn't know. There is a second red spot that formed in 2003. These are, in the infrared, strong emitters of infrared radiation. There's a lot of heat escaping from Jupiter's atmosphere through the Great Red Spot and through Red Spot Junior, okay? Let's see, they showed this in the infrared camera demo. We've got the pillar in Carina. All right, if you want to see it in infrared, all of this blue gas in the background turns transparent, and you have tons and tons and tons of stars. If we look in visible light, there's a star forming right there. You can see a little bit of a jet-like material here, but if you go in infrared, boom, there's that star that has just been born. Here are the jets coming off of it in detail. Infrared is a great, because of its longer wavelengths, looks into these dense clouds, sees more detail inside these dense clouds. It is great for studying star formation and also planet formation. Not as good as the microwave, as I showed you with the HL Tauri, but it's really good for looking into these dense clouds that are opaque to visible light. Let's see, what else do I have for infrared? Oh, of course, we got to bring the Whirlpool Galaxy in. I told you we'd come back to the Whirlpool Galaxy and these dark, dense clouds. We showed you how the densest regions show up in microwaves. Slightly less dense regions show up in infrared, but man, do they show up. All right? You're seeing this is the gas and dust in the galaxy. Here you're emphasizing the stars in the galaxy, and the gas and dust just shows up as a little bit of darkness. Let's get rid of those stars. Let's just look at the gas and dust. Isn't that cool? All right, gives you a whole new view of the Whirlpool Galaxy. You can see the gas and dust structure that's underneath those visible light stars. All right, I mean, I almost like to say it's like taking an X-ray of the galaxy, but it's taking an infrared ray of, yeah, it doesn't work. Sometimes your analogies just get in the way. All right, so that is infrared light. We did visible light to start with. Now we jump to ultraviolet light. Visible light is 400 to 700 nanometers. So infrared left off at 700, 400 to 700 is visible. Now we go ultraviolet light, 400 nanometers down to about 10 nanometers, okay? Higher energy than visible light. What do we think of when we think ultraviolet UV radiation? We think of going out to the beach and going out in the sunshine. Okay, got to protect ourselves from the sunshine. Well, the UV radiation. There are some glasses that I found called Zero UV. They have such great UV protection. Your eyes will be protected from all of the ultraviolet light from the sun. Here is a poster from the Vision Council on a lifetime of UV eye protection. All right, so your kids know about UV radiation and UV protection, even if it's not something that they think they associate with ultraviolet light. Okay, for Earth, actually, it isn't really that much of a problem. Okay, because if we look at this diagram, which shows the penetration of light through Earth's atmosphere, here is ground level, here is the top of space. You can see that visible light gets through and a little bit of ultraviolet radiation gets through, but most ultraviolet radiation is actually blocked by Earth's atmosphere. Okay? Something to know, most ultraviolet radiation from the sun is blocked by Earth's atmosphere. If that wasn't true, we'd be wearing UV radiation all the time and much higher SPFs and much higher UV protection in our sunglasses, okay? So be thankful that most of it is actually blocked, okay, because we only have to worry about a little bit of the ultraviolet when we go out in the sun. That also means, however, to do ultraviolet astronomy, we can't do ultraviolet astronomy from the ground. We have to go into space to do ultraviolet astronomy. All right, the most famous ultraviolet object, we looked at it before in our thing, is the sun. This is what it looks like in visible light. Here's what it looks like in 4 ultraviolet wavelengths, okay? These sunspots here, okay? Each of these sunspots is larger than our entire planet, all right? The sunspots are generally 10,000 to 20,000 kilometers across. Some of them up as high as 40 and 50,000 kilometers across. All of these sunspots, larger than our entire planet. They are intense concentrations of magnetic fields. Those magnetic fields can have lots of energy and emit in wavelengths in the ultraviolet. And so all of these bright spots here are places where there are sunspots in visible light. So the dark spots in visible light are bright in ultraviolet light. And so this is like the 304 angstrom all the way going down to, I think this is like 171 angstrom, okay? The various band passes, and they use multiple ultraviolet wavelengths to tell us about multiple temperatures in the atmosphere of the sun, okay? Saturn. Does Saturn emit ultraviolet light? Saturn itself doesn't emit ultraviolet light, but what does this look like here? That looks like an aurora. There are aurora on Saturn. Okay, we have aurora on Earth, but unlike the aurora on Earth, the aurora on Saturn are only visible in ultraviolet radiation. Okay? They don't have visible light radiation from their aurora. They have ultraviolet light radiation. So this image here is a combination of, first of all, 3 images in visible light of Saturn plus 3 images in ultraviolet light of Saturn. What Hubble discovered with this series of observations was one that, yeah, even though Saturn's 10 times farther from the sun and the solar wind will be 1/100th the density it is at Earth, there's still an appreciable aurora on Saturn. The other thing is that these images were taken 2 days apart, and you can see how variable the aurora are. We thought the aurora on Saturn would be relatively smooth because it's further out, low density and everything. We were wrong, okay? It's nice to, actually, it's really good to know when you're wrong, okay? It's really good because it tells you that there's new physics, there's more to the story than you suspected, okay? So there is ultraviolet coming from Saturn, it's coming from the aurora. All right? Galaxies also emit in ultraviolet. Ultraviolet is higher energy. We talked about the brightest stars having lots of ultraviolet light because the peak of those brightest stars will be in the ultraviolet. So when you look at a galaxy, you would expect to see the brightest stars, and you do. What you see are these clumpy regions where is the places where these newborn stars have formed. Okay? The brightest stars are the most massive stars that live the shortest lives. So these stars only live for tens of millions of years, therefore they never spread out across the whole galaxy. They're all clumpy. They always start off in those star-forming regions and they die in those star-forming regions. So before they have a chance to migrate out and see the world, they explode as supernovae. So these are your clumpy star-forming regions with these high-energy stars in ultraviolet in galaxies. All right, 2 more regions. X-rays, starting at 10 nanometers down to 0.01 nanometers. So nanometer scale, you get X-rays. And of course, we all know about X-rays from having been to the doctor. All right, can you see the break in this person's forearm? All right. Now, are the bones emitting X-rays? No, they are not. Are the bones absorbing X-rays? Shake your head. Yes, they are, okay? What some kids fail to recognize is that you are studying the bones in shadow. They are printed as a negative of that, but this is the shadow of the bones. Your skin and your soft tissue allow X-rays to pass through. Your bones actually absorb some of the X-rays from the machine. All right? So the bones are actually dark in X-rays. We print it in reverse. You get the bones glowing, and you can see the shadow of the X-rays in order to see the details of the bone structure. Got it? Okay, cool. All right, so X-rays look at things. The sun was really bright in ultraviolet. It's also really bright in X-rays. Okay, so higher up in the atmosphere, you can see all this. You can see million-degree temperatures. We had tens of thousands of degree temperatures for ultraviolet, millions of degree temperatures for the X-rays. And what's really cool is the Yoko satellite followed it for a bunch of years, and you can actually see the solar cycle taking place. This is the changes in the X-ray view of the sun from 1991, where it was active, all the way to 1995, where it became quiet. All right, the sun goes through these cycles over the course of 11 years. Well, it's actually a 22-year cycle, in terms of which it gets active and then it gets quiet. It gets active and it gets quiet. Okay, this is kind of cool, the X-ray image to show that. I told you we'd come back to the Cassiopeia A supernova remnant. I showed you previously the external part where the radio emission was coming from. If this is a supernova explosion, then the stuff internal should be heated to really high temperatures. So high that they don't radiate at visible light. They radiate beyond visible light. They actually show up really beautifully in X-rays. This is an X-ray image of Cassiopeia A. In visible light, you see the stuff at thousands of degrees. In X-ray light, you see the stuff at hundreds of thousands to millions of degrees. All right? One of the simplest way to look at how, when we look at different wavelengths, what we understand is we're seeing different temperatures. The longer the wavelength, the lower the temperature. The shorter the wavelength, the higher the energy, the higher the temperature. X-rays being a high energy thing, we'll see things at hundred thousands to millions of degrees temperature. All right? We also can look at clusters of galaxies. And you might say to yourself, why would a cluster of galaxies emit X-rays? It doesn't. The cluster itself does not emit X-rays. But when you gather all these galaxies together, each galaxy has its own associated gas halo. All right? And so you bring these galaxies slamming together, and these halos come slamming together. This low-density gas comes smashing together at high speed. That gas collides and heats up. And there's so much of it, and these galaxies are moving at projectile velocities, all right, that the gas heats up to millions of degrees. So this blue image here shows you where the galaxies are in terms of the mass of the cluster. All right, this pink image here shows you where the X-rays are emitted. Okay? This is that high temperature million-degree gas that's spread throughout the cluster of galaxies. And so if you go to the Chandra website, you'll see a lot of images that look like this, where you've got the Hubble image that shows you the visible light view of the galaxies. You've got this blue, so it sort of shows you how if we interpolate that to being the mass of the cluster, and then the pink, which shows you the X-ray gas. Okay, the X-ray gas traces pretty well the mass of the cluster, because wherever wherever the mass goes, you bring along the halos heat up to this million-degree stuff. X-ray gas is a way of tracing the true extent of the cluster. Matter of fact, I should have included one here, but sometimes you have these clusters where the galaxies have passed through one another, and you've got a clump of galaxies here and a clump of galaxies here, and you've got this big X-ray halo in the center because the galaxies pass through, the gas collides and heats up and puts the X-rays out in the center. All right, gamma rays, last thing, because John's looking at me like, it's 3:30, Frank, you got to finish up. Well, don't worry, we'll get there. All right, anything less than 0.01 nanometers, okay? On Earth, can we produce gamma rays? Yes, you see them all the time. They can be produced by lightning strikes, okay? Lightning strikes can be energetic enough to produce gamma rays. An appreciable amount of gamma rays? Not really, okay? You're not going to see tons of gamma rays. If you are really getting gamma rays, you need some nuclear reactions, and of course, something like a nuclear explosion would do that, all right? This is a picture of a nuclear test explosion from the 1960s, if I remember. I can't remember. But that's where we would get gamma rays. And if you were trying to turn into the Incredible Hulk, I guess you'd have to be involved in this in some way, right? That is unfortunately the way most kids relate to gamma rays, is the Incredible Hulk or other superheroes like that. Or I guess the Fantastic Four is coming out yet again. So yeah. No known evidence for turning into Hulks or the Human Torch or whatever. Okay, this is, however, how astronomers do see gamma rays, okay? They are few, they are far between, they are exceptional. But if you look at the entire night sky, this is a hemisphere of the night sky using the Fermi Large Angle Telescope. And then there was a sudden boom of gamma rays. It was a burst of gamma rays. So we astronomers call it a gamma ray burst. We're pretty straightforward, as I said, okay? So this is the gamma ray burst called 130427A, which I can tell you occurred in 2013 on April 27th, and it was the first one discovered on that day, which is how we name them right here, okay? So it occurred here. And so we see these bursts of gamma rays across the sky, all right, about one per day, and we have studied them, all right? And so we have seen lots of them. The Batsy experiment on the Compton Gamma Ray Observatory has over 2,000 of them, all right? And we wonder, what the heck are these? All right, by the way, they were discovered back in the 1960s by the military. We were looking for nuclear explosions. They wanted to see how many nuclear bombs are the Russians or other countries exploding, right? So they were looking for these test explosions, and suddenly they started to see one every single day, all right? And they're going, they didn't know what it was. It couldn't possibly be a nuclear arsenal because people didn't have that many nuclear bombs to explode, right? And they realized it was coming from the sky. All right, they didn't tell us astronomers because it was classified, but eventually we found out ourselves. And so we assumed that they would be nearby, because if you're producing gamma rays, which is really high energy, and that's got to traverse the universe, you know, it's going to be a nearby explosion, right? Actually, we don't see any trace of the galaxy here. All right, we would expect to see a concentration along the galactic plane if they were nearby. This plot shows you these gamma ray bursts are really, really far away. Here's the current SWIFT satellite with 500 of its gamma ray bursts. Again, no concentration on the Milky Way's galactic plane. They come from everywhere on the sky. We believe that they are, in fact, cosmological in distance. These are hypernovas. We talked about supernovas, okay? Hypernovas are the highest energy supernovas that we can imagine so far. Maybe we can learn to imagine more. And they actually occur at great, great distances. So here is an image of one of the optical counterpart to a gamma ray burst. Okay, is it obvious which one it is? No, it's not. It's actually that little dot right there. Okay, that turns out to be a galaxy, very, very distant galaxy, in which you have this extremely rare event occurring, and it's visible across the universe. Okay, these are explosions so large they can be seen across the universe. Here, by the way, are the optical counterparts to several gamma ray bursts, and you can see that they are all these very, very distant galaxies. All right, so we have, in gamma rays, we see a lot of these gamma ray bursts. We can also look at the all sky for gamma rays. And in all sky, we mostly see pulsars and quasars, okay? So pulsars would be those like the Crab Nebula, where you have that neutron star, and quasars would be these distant galaxies with supermassive black holes, okay? So that's very few things that emit at gamma rays. But it's still, we can look at the gamma ray sky. You can definitely see the plane of the Milky Way when we do an all-sky map in gamma rays. All right, so just to finish, let's talk about a few multi-wavelength montages that you will find out on the internet. We looked at the Crab. Did we look at this one? We saw one version of the Crab Nebula. Here's another version of the Crab Nebula, from X-rays down to radio waves with multiple infrared wavelengths. So this probably comes from Cool Cosmos if it's got this many infrared wavelengths. Okay, and on that, we've seen that. Emphasizes that we have 3 great observatories: the Hubble Space Telescope in visible light, the Chandra X-ray Observatory for X-rays, and Spitzer looking at infrared. As I mentioned, we also had the Compton Gamma Ray Observatory. That was one of NASA's great observatories to look in gamma rays. We got the SWIFT and the Fermi missions that are doing that now. If you look at the 3 main ones, sometimes the visible light is the wimpiest of the images. The infrared produces better, and the X-rays produce even more. This is a supernova remnant, okay? Visible light is kind of blah for supernova remnants. You really want to study supernova remnants, you go to X-rays, okay? The expansion across the electromagnetic spectrum has enabled lots of new astronomy. For example, here again is a triptych of Hubble, and then the infrared version where you see that gas and dust and these bright star forming regions, and then the X-ray version where you see only the high energy things on that. And that is one of the great legacies of NASA's Great Observatory Program, that we study high resolution images across the spectrum with the great observatories. Finally, I will leave you with the multi-wavelength Milky Way. This was a poster put together here at NASA where you can see gamma ray, X-ray, optical, and several infrared bands, this molecular hydrogen, atomic hydrogen, and radio from the plane of our Milky Way. And you can see that when we look at that at certain wavelengths, we can see how thin our gas and dust disk is as we look on it. Because with the Whirlpool galaxy is a face-on spiral, ours is an edge-on spiral. We see only the pancake oriented sideways to us, and you can see the gas along in here. So, finally, the idea is that astronomy, one of its greatest achievements of the last 100 years, is astronomy going from just what the human eye sees to going across the entire electromagnetic spectrum. All right? It allows us to look in different wavelengths to see different characteristics of objects, and really has expanded our understanding and view of the universe. All right, thank you very much. Thank you.